Right, so now that you have somewhat of an understanding of what a derivative is and how it relates to the slope of a graph in general, we're going to look at some specific types of functions and how we calculate the derivative for those functions. So we'll look at polynomials, we'll look at trig functions, and then we'll also look at exponentials that have an e in it. The most important one is the polynomials, and that's what we'll spend the most time on. I also want to mention that there's a pattern we need to know for motion functions, and that is that if you are given a function that describes the position of an object, when you take the derivative of this, when you look at the rate of change of the position, that will change or transform that position function into a velocity function. And if you do the process one more time, what we're going to be talking about in this video, it changes that velocity to an acceleration function. So not all functions, not all cases we use derivatives follow this pattern, but it is super important and it happens more than any other pattern. So let's look at some examples. Again, we saw this pattern in the earlier video, but if we are given a function x as a function of time, then we can compute the derivative, which we would write like this, dx dt. That refers to a small change in x versus a small change in time, or the rate of change of x. And again, the rule is that if there's no exponent in the t term, then we just drop the t entirely, and the derivative is 4. And then we have two things added together, so we would individually think about the derivatives of each part. Since 11 is just a constant, and we're looking at rates of change, then there is no value for that, it's just 0. So dx dt would be 4. In this next one, we are looking at a function of v. So when we calculate the derivative, it is giving us a dv dt. That is not a notation that is stressed as much as I'd like to see it in calculus classes, but we use it a lot in this class because we can see now that when we calculate that derivative, it's a velocity over a time, meaning it's going to be an acceleration. We can understand the meaning of the derivative, which is really important. But let's go ahead and remember how to calculate it here. So we're going to look to see that the exponent is a 2, and we'll multiply that by this coefficient, so we get 18. And then what we do is we drop the exponent by 1. So everything becomes a little less complex as you take that derivative. So it goes from t to the 2 to t to the 1, or we can just write t. The next term here is negative 7t. So the same way we dealt with the 4t up here, this is just going to be negative 7 when we take the derivative. And then 3 is a constant, so that will drop out as we do this process. This next function is a function describing a force. And notice that the variable has changed in the function. It's x instead of t. And we'll see that later when we get to some other ideas that force functions can relate to positions as well as times. So df dx would be the derivative that we would be calculating here, but the process is the same. We look at the exponent, which is a 4, times this coefficient. So 4 times negative 0.45 would be negative 1.8. And then we lower that exponent from x to the 4th power to x to the 3rd power. Just subtract 1 from the exponent. And then we have another term here. So here the exponent is 3. So again, we're going to multiply that by the 3.2. So that's going to be 9.6. This exponent drops by 1, x to the 2nd power. All right, and the last one here doesn't seem to follow the pattern at all. We got the exponent, or we got the variable in the bottom of the function. So the first thing we're going to want to do here is actually sort of transform that function into something that looks a little bit more like what we've been noticing in other problems. So I'm going to rewrite this as 3t to the negative 2. Okay, I'm going to bring that exponent up so that it looks more like what we're used to seeing. and then I'll just follow the rule. So I've got -2 as my exponent, so -2 times 3. I should write my dp dt first here. All right, so -2 times 3 is going to give me -6. And then I have to lower my exponent by 1. So that goes from -2 down to -3. You're subtracting 1. And then some people would, in the end, rewrite this as -6 over t cubed. Either way is correct. All right, so trig functions. This is another type of function that we'll see in our class. Not as much in the first semester, more in the second semester, but still we want to kind of preview it and know it's out there. So this rule is a little bit different. One thing to keep in mind is that when you see a cosine function and you take the derivative of that, a really important thing is to see that it actually switches completely to a sine function, and it also picks up a -1. So the basic idea is that if it were just cosine of t, the derivative of cosine of t would just be -sine of t. But if it's a sine function already, and you take the derivative, then it switches to the cosine, but it doesn't pick up that negative. And those are going to be tricky rules to sort of remember sometimes, especially if you don't use it very often. But these rules are summarized on the formula sheet. We'll talk about that in class. All right, so when I take the derivative here, dx dt, derivative of the position function with respect to time, what I'm going to do here is I'm going to switch it to a sine function. Okay, so that's going to be part of it. I'm going to keep the 4t. Can't change what I'm taking the sine of, but I'm going to take the derivative of this, what's called the argument. So the derivative of 4t would just be 4, and I'm going to multiply that by the 6. So the number in front is going to become 24. And again, the process of taking the derivative of a cosine function picks up a negative sign. We'll see later on an example of why that makes sense in a real-world situation. The next one here, dx dt, for this function, it's a sine. So again, it's going to switch to a cosine. But I'm going to keep the 7t the way it is, so that part of it stays the same. I take the derivative of 7t is just 7. Multiply that by 10, so there's a 70 in front here. Let's do it again. dx dt. This is cosine, so I'm going to pick up a negative. So it's going to be negative, and it's going to be 12 sine of 3t. Okay, I'm going to switch to from the cosine to the sine and pick up a negative. And then I'm going to keep that argument, the 3t, the same, but I'll take the derivative. 3 times 4 is 12. And the last one here, usually the numbers are going to be messier like this. It's going to have some decimals in it. This is already a sine function, so when I take the derivative, it switches to the cosine, but we keep the 5t. And then we take the derivative of 5t, that is 5 times 1.2 is equal to 6. And then, again, this was sine. When I switch to the derivative, it just, I don't change the plus or minus part of it. Last function, real quickly here, is exponentials. And this we don't see very often at all. There's just this one little application that it's important in our class. But again, I want you to see it in advance so that when we encounter it, it's not brand new. This rule, again, you kind of look at this right here, and you're going to end up taking the derivative of that. So a 3 is going to be important. Now with the sine and cosine, we switched between sines and cosines when we took the derivative. With this e function, you actually just leave the function exactly the way you see it. So if I see e to the 3t, I leave it as e to the 3t, and I just change the number in front. So the derivative of the 3t is 3. 3 times 4 is 12. That's going to be the number in front. Let's do another one here. So this one would be a dv dt because that's what my function is describing. So again, the e to the 6t, that part stays exactly the same. but I take the derivative of 6t is 6, times 2.5 is 15, so that's going to be my number in front.